Welcome, focused learners, to another exclusive explainer. Today, we're talking about 90 minutes to glory. This is your game plan for exam victory. We're diving deep into the Cambridge IGCSE's Physics syllabus, specifically code 0625, and we're honing in on Chapter 6, Energy Stores and Transfers. Think of your upcoming exam exactly like a championship match. You can have all the raw physics facts crammed in your head, but if you don't know the rules of the game, or if you rush and miss the specific requirements of the command words, you are literally leaving easy marks on the table. Today we're looking at how mastering the concepts of energy stores and understanding the precise language of physics is your ultimate game plan. We're going to transform the way you analyze questions, turning those frustrating red pen marks into green check marks. We'll decode exactly what the examiners are actually asking for. So, let's get focused. Here's our roadmap to mastery for today. We're covering 6 absolutely crucial areas. First, energy, the ultimate currency. Second, stores versus transfers. Third, tracking energy flows. Fourth, the law of conservation. Fifth, efficiency and wasted energy. And finally, exam equations and strategy. It's a packed game plan, so let's jump right in.
Section 1. Energy, the ultimate currency.
Okay, let's dive right into this. To truly master physics, we have to start with a fundamental analogy that grounds this entire chapter. Energy can be kind of an abstract concept, but the Cambridge coursebook gives us a brilliantly simple way to visualize it. Energy and energy transfers are involved in absolutely everything from a sprinter waiting at the starting block to a massive power station lighting up your entire city. But to secure those top marks, we need a rock-solid idea of what energy actually is at its core. I absolutely love this analogy from the text. Imagine that energy is like money. The amount of money you have determines what you can buy, right? Well, the amount of energy you have determines what you can do. Let's imagine that the total amount of cash I have is completely fixed. I can't magically print more out of thin air, and I can't permanently destroy it or spend it into a black hole. Some of my money is sitting securely in my bank account, some is in my physical wallet, and hey, maybe some is lost on the back of my sofa. I can transfer or move this money between these different places, but the total amount of wealth I possess, it doesn't change. Energy works exactly the same way. It's a fundamental quantity that must be changed or transferred to make literally anything happen.
Section 2. Stores versus transfers. Let's see how this builds. Now that we understand our energy money is a fixed amount, we need to transition into how we officially classify these accounts and transactions in the formal language of physics. And hey, before we break this table down, make sure you subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button right now so you don't miss out. Okay, so in the Cambridge syllabus, examiners are incredibly strict about the difference between where energy is kept and how it gets moved around. If you mix these up, you lose marks, plain and simple. We have energy stores, which are your bank accounts, kinetic energy for a moving object, gravitational potential energy for something raised up high, chemical energy locked in fuel or your muscles, elastic energy in a stretched band, and your nuclear, internal, and electrostatic stores. Then we have energy transfers, which are the transactions, electrical, thermal, radiation like light, and mechanical work. Now I need to issue a massive warning here. This is a classic trap. Do not confuse internal energy with thermal energy. Actually, let me repeat that. Internal energy is a store. It's the total kinetic and potential energies of the particles inside an object. Thermal energy is a transfer. It's energy traveling from a hotter place to a colder one. Heating something up transfers thermal energy into it, which then raises its internal energy store. Like steam has more internal energy than boiling water, even at the exact same temperature, because the water molecules in steam are further apart, giving them a bigger potential energy store. Knowing this distinction is a real game changer for the exam.
This brings us to another key distinction examiners love to test: event versus process. Energy is only transferred or changed during specific events and processes. In other words, when something actually happens. An event is something sudden, taking place at a specific time and place. Think of striking a match or a car crash. Boom, it happens. A process, on the other hand, is a series of actions taking place over a period of time. So the burning of that match after it's struck, that's a process. Climbing a mountain is a long process, while suddenly tripping and falling over would be an event. In the exam, you'll likely be asked to identify if an energy transfer is occurring due to an event or a process, so keep these definitions sharp in your mind.
Section 3. Tracking energy flows.
We know the stores, we know the transfers. Now we need to visually map out these physical transactions using energy flow diagrams. Cambridge loves these diagrams because they prove you understand exactly how energy behaves in a real-world system. Let's walk through an excellent example, mapping the energy stores and transfers of a battery-powered lamp. We start with the battery, which is a store of chemical energy. The energy is transferred electrically to the light bulb. The light bulb's store of internal energy then increases. From the light bulb, energy is transferred via radiation, specifically light energy, straight to the internal energy store of the surroundings. Mapping it out like this takes a complex sequence and makes it incredibly logical to follow. Now, what's really interesting here is spotting where things go wrong. Where exactly is the energy being wasted? If you look at the light bulb stage, you have the useful transfer of light radiation, but there's also thermal energy, or heat transfer moving into the internal energy store of the surroundings. That thermal energy is completely wasted. The text gives a super cool example of scuba divers using flashlights at night. The chemical energy in the battery transfers electrically to the bulb, increasing its internal energy. The lamp transfers useful light, but also wastes energy by heating the cold water around it. For divers deep underwater who literally cannot plug in and recharge their batteries, having an efficient flashlight that minimizes this thermal waste is absolutely crucial. Section 4. The Law of Conservation. Now we transition to the ultimate, unbreakable golden rule governing every single transaction we just tracked. This is the principle of conservation of energy. You need to memorize this exact definition. Energy cannot be created or destroyed. It can only be stored or transferred. It is the absolute bedrock of physics. In any transfer, the total amount of energy before is exactly equal to the total amount after. Let me be really firm about this. If your calculations before and after don't add up perfectly, you must act like a strict auditor. You are missing something. And hey, speaking of not missing out, stop scrolling. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to Ace the Exams_IGCS and turn on all notifications. All right, back to our auditor mindset. The coursebook gives a great example of a car burning 300,000 joules of chemical fuel per second. If it only gains 130,000 joules of kinetic energy and 70,000 joules of gravitational potential going up a hill, where did the missing 100,000 joules go? It didn't vanish. It transferred away from the car as thermal energy into the surroundings. You always have to balance the books. Section 5. Efficiency and wasted energy. That idea of energy escaping unnoticed leads us directly into 2 critical exam topics, efficiency and wasted energy. Because energy is always conserved, any energy that doesn't end up doing the specific job we want is considered wasted. Calculating just how much is wasted versus how much is useful is the whole point of efficiency. To brilliantly illustrate this, we use a Sankey diagram. This is a specific flow diagram that visually proves the conservation of energy. The absolute key to reading these, the width of the arrows is directly proportional to the amount of energy. If we look at a classic 100-watt light bulb, we start with the total energy input on the left. Then we see a split. A tiny arrow points forward representing the useful light energy. But look at the massive, thick arrow pointing down. That represents the vast majority of the energy dissipating as wasted thermal energy. At a single glance, a Sankey diagram shows you just how incredibly inefficient a system really is. So let's lock down the formal definitions your examiner wants to see. Efficiency is the fraction, or the percentage, of energy supplied that is usefully transferred. When a transfer is less than 100% efficient, which, let's be real, is almost always, the wasted energy is described as being dissipated. This just means it spreads out into the surroundings, usually as thermal energy, raising the internal energy of the room or the environment. And once it's dissipated, it's pretty much impossible to get that energy back in any useful way. The text notes a fascinating fact. Even the most modern gas-fired power stations are only about 50% efficient. That means literally half of all the chemical energy supplied to them is utterly wasted, just dissipated into the air. Pretty crazy to think about. Section 6, Exam Equations and Strategy. Okay, let's shift into our final masterclass mode. We are focusing purely on exam strategy and equations now. Specifically, we have to decode the exact command words Cambridge uses. Because, look, understanding the physics is only half the battle. Giving the examiner exactly what they're asking for in the exact format they expect is how you secure the bag and guarantee top marks. Let's break down the 3 big ones. First up is the command word state. The official definition is to express in clear terms. When a physics question says state, they want a direct, factual, punchy answer. No long-winded essays, no paragraphs. If a question says, state the equation linking kinetic energy, mass, and velocity, you literally just write down the formula. That's it. Grab your 1 mark and move on. Don't burn your precious time over-explaining a state question. Next, we have calculate. This means to work out from given facts, figures, or information. When you see calculate, it's time to bust out the equations, and you absolutely must show your working steps clearly. The coursebook features a classic problem involving a ballistic pendulum where a projectile hits a block. If they say calculate the kinetic energy of the block, state the formula, substitute your numbers, do the math, and write the final answer with the correct units, usually joules. Showing your work is a safety net. It guarantees partial marks, even if you have a slip of the finger on your calculator right at the end. Speaking of calculations, these are your essential formulas. Kinetic energy equals 1/2 times mass times velocity squared. And the change in gravitational potential energy equals mass times gravitational field strength times the change of height. Now I need to remind you of a brutal trap that trips up so many students. When calculating kinetic energy, be extremely careful, only the speed is squared. A super common mistake is multiplying the mass and speed together first and then squaring that whole number. No way! Do not do that. Start by squaring the speed on your calculator. Then multiply by the mass, then divide by 2. Think of a 2,000 kilogram van speeding up from 10 meters per second to 20 meters per second. Because the speed doubles, the kinetic energy doesn't just double, it increases by a factor of 4. Because that speed is squared, you have to remember that relationship. Our final command word is suggest. This means applying your knowledge to situations where there are a range of valid responses to make proposals. Basically, suggest requires you to think outside the textbook. Going back to that ballistic pendulum, the block swings up and gains gravitational potential energy. The question asks you to calculate max height. But then a follow-up says, it might not be easy to measure the height increase. Suggest another variable a researcher can measure more easily and use to get the height. The examiner isn't looking for one magical right answer. They want you to act like a real physicist solving a real problem. You might suggest measuring the angle of the pendulum swing or the horizontal distance. It's about applying what you know to a fresh scenario. I want to wrap up by challenging you with a reflection question pulled straight from the source material. If you do not know the difference between an event and a process, how are you going to find out? This gets to the absolute core of exam mastery. You have to take active control of your learning. Don't just passively reread your notes. Test yourself. Can you draw an energy flow diagram for a catapult? Can you explain why steam causes worse burns than boiling water using internal energy? The championship final is won in practice. Students who implement these specific physics strategies see an average improvement of 2 whole grade boundaries, but only if they practice consistently. So here is your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Also, drop a comment below with your target grade for physics and the biggest challenge you're currently facing. Our team responds to every single comment. Like and share this video with your study partner. Ace the Exams, your Cambridge success starts here.